Let's look at a very interesting problem here. So the problem goes like this. So what we have is we have a railway network with a collection of stations. So maybe our network might look like this, where this can be called as a railway network. Now within this railway network there are multiple stations, so we can mark this as S1, S2, S3, S4 and S5, and all of them are connected to each other through rails. So you can consider it as a very basic, very normal railway network where where there are different stations within the network and they can be connected to each other through rails. So that is the problem here. What we are trying to do is that like every stations can be marked. So these are called stations, right? Now the problem says that every station has a particular volume assigned to it, or a volume of people assigned to it. So we'll assign every station a particular volume. So let's say V1, let's say V2, V3, V4 and V5. So by this we can say that a station S1 has volume V1. So volume V1 means it has V1 amount of people visiting this particular station on a daily basis. That's what we can assume. Now what the problem asks for is that we have to select stations. We have to pick stations from the network in a way that the sum of the volume of people can be maximized. So what we have to do, we have to basically maximize the sum of volumes of the selected stations. Now there is a catch here. There is a way to select stations. So the problem says that if you select a particular station, then you cannot select their adjacent stations, right? So one of the example is that if I go ahead and pick up station S1, then I cannot pick up all of these stations. These stations cannot be selected. That is the overall problem here. We have to select stations in such a way that the volume of the people of the selected stations, the sum of the volume can be maximized, and I can only, if I select one of the station, I cannot select the adjacent one, right? And so by maintaining the rule, or by following the rule, I have to select the stations in such a way that so that we can maximize the sum of the volume of the people. Now we have many interesting things to note here, which is already given in the problem. So the first thing that the problem says is that all the stations are connected to each other, or basically we can mention here that stations are always connected. So by saying this, the problem means that there is only single component within the graph. That is the problem here is saying. So we can say that the entire graph is a connected component. Now another thing which a problem states here is that there is always exactly one path between two stations, right? So these are the two things which is like important to note here, right? So there is always one path between two stations, meaning that there cannot be any cycles. So I'm going to show you here. So suppose there is station S1, there is station S2 and there is station S3. Now suppose there is a single path from S1 to S2 and from S2 to S3, and now suppose we have a cycle here, right? So you can see that there is a cycle here. So if it is a cycle, then there can be multiple paths, right? So if I have a cycle here, then I can say that from S1 to S3 I have two paths. First is following this one and then following this one, and this cannot happen because it has already been given that there is only one path between two stations, meaning that there cannot be any cycles. So I'm gonna write it here. So no cycles. So if we look at this problem, it says that the graph is connected and there is only one path between two stations, meaning there is no cycles. So initially it looked like it's a graph problem, or basically it looks like the structure which we currently have is a graph, but now we can say that it's not only a graph but it's also a tree, because like tree is a kind of graph, right? And we can safely say that it's now a tree because all the stations are connected to each other and there are no cycles, right? So if I'm gonna scroll it down here, so our structure looks something like this, right? I'm just building up an array tree maybe, right? So our structure looks something like this, where we have multiple stations connected to each other, where there are no cycles, or basically there is always one path between two stations, and all of them are connected to each other. So this is the structure which we will be which we're gonna follow in the solutions ahead, so that we can build up a clear solutions. So now we have a more designated design here, right? We have a tree, and as the problem mentioned before, that if you gonna pick one of the node, then you cannot pick the adjacent node. So that is one of the example. If I go ahead and pick S4, then I cannot pick S9, S10, S11 and S1, because these are their neighboring or the adjacent nodes. And to find out a solution for this problem, so I'm gonna again draw a better tree structure so that we can look at this problem. So suppose we now have like suppose we have a structure like this, where these are stations, and I'm gonna fill up these station nodes with the volume of people it can hold. Suppose this is 5, this is 8, this is 10, this is 13, this is 3, this is 11, this is 24, this is 9, this is 6, and this is 17. Now how we can pick up the nodes so that the volume can be maximized? So one of the things can be that we can like follow a simple greedy approach, where we pick up those nodes which has maximum volume of people. So I can go ahead and I can pick up this node, and I can pick up this node, I can pick up this node, right? So that I can make sure that the volume is maximized. But the problem here is that if I'm gonna pick up this node, then I can never pick this node, right? If I'm gonna pick up this node, I can never pick up this node. So I can go ahead, I can follow a greedy approach, but that will not gonna actually solve our problem. Because hey, suppose if I go ahead with a greedy approach, and there is a tree design something like this. Okay, so there is one node and there are 3 nodes attached to it, and suppose that this node has 50 as a volume, right? But the rest of the nodes are 25, 25 and 25. So this is one of the subtree, right? There can be like this structure can be way bigger, but I am just concentrating on one of the subtrees. And according to the approach we designed, like the greedy approach, if we went ahead and picked up this node, because obviously this one has the highest volume, so if I go ahead and pick up this node, I will not be able to pick these. So the problem here is that even though I am getting 50 volume of people, I'm also losing minus 75 volume. And how? That this is the 25, 25 and 25. I'm losing these 75 volume of the people. So it's not always that, it's not sure that this greedy approach will work, because like even though you pick the node with maximum volume of people, you might end up losing other nodes which can sum up and give you a better result, right? So that is one of the reasons that why our greedy approach will not gonna work here. Now we discussed that our greedy approach is not working, so how we can like find the solution. So the solution for this problem is basically we'll gonna perform DP. So this is what this entire video is all about. We're gonna perform DP on trees, right? This is a tree structure. We're gonna perform dynamic programming, and that's why it's a great solution, because it covers dynamic programming on trees. And how we're gonna do that, let's discover. So again, I'm gonna draw the same structure, the tree structure of stations which we have followed from the start. So now the problem here says that if I'm gonna pick up a particular station, I cannot pick up their adjacent node. So accordingly, what can happen is that suppose this is one of the subtree, and there are 2 ways I can pick up the node, right? First is I'm gonna select the topmost node, and in that case what will happen is that I'm just talking about this subtree. So if I select this node, then I cannot select these 2. This is first way. And the second way is that if I am gonna select, if I do not select this one, then I have the authority to select this one, right? So these are the two ways in which I can like follow at a particular stage. So I can either pick this one or I can not pick this one. There are two ways. If I can put this in my solution list, or I can not put that in my solution list as well. Now if I follow the first way, there will be a different solution, right? If I follow the second way, then there will be a different solution. And what we have to do is that at each node we have to compute this. So the first thing is that what can be the maximum volume if that particular node is included, right? If that particular node is included, and what is the maximum volume if that particular node is excluded, right? So this we have to compute at each and every point of time, or at each and every node when we visit that, right? And when we have both of them, we can pick the maximum among these two. So this, suppose this is value dp, maybe we can say d1, and this is d2, then at the end we're gonna return max of d1 and d2, because we are always concerned about maximizing the volume, right? Any way possible, either by picking that node or not picking that node. And that is our DP approach will look like. We have understood that we need to follow a DP approach, but how to come up with a DP expression so that we can make sure that our solution goes well. So again, I'm gonna draw the same tree structure here, and this time I'm gonna only draw a particular subtree to see this, so that we can see clearly how we can devise a DP approach. So the first thing here is that at every node we will have a DP array, and this DP array will be a two-dimensional array, right? So this DP will have a DP0 value and a DP1 value. DP0 will be the maximum value of that particular node when it is excluded, and DP1 will be the maximum value of the particular node when it is included. And suppose we have our station with n number of, there are n stations in our network, then our DP solution will look like this, dpn2. That's because for every node we will keep two values, that is 0th value, or the first value is when that particular node is excluded, the second value when that particular node is included. Now the question is that how you compute. So suppose if you are at a particular station I, then how you compute dpi of 0 and dpi of 1. Now you compute this by performing a DFS approach, and you make sure that whenever you are at a particular root node, you have the solution for their children sorted, right? So suppose if this is a particular node I, right, what we can do is that dpi of 0 will be the solution where we are not selecting this particular node, right? In this way we can either select this node or we cannot select this node. We can either select this node, we cannot select this node, we can either select this one or we cannot select this one. Why? Because it is not guaranteed always to select this node, because there can be a better solution ahead as well, right? So since all of these are already computed, we have computed the DP for all of these three children, we can pick the best one, right? So how you pick the best one? You can pick the best one by maximizing the two values. So what you will do for DP of 0, it will be the sum of all the children, right, or all the adjacent node, where we will do the DP of, suppose this is one of the children, maybe j is the children, dpj of 0 and dpj of 1. Now I want you to take a look at this expression. What does that mean? So if j is the collection of the adjacent children, or basically the children of this particular station I, right, basically the adjacent station of this particular station I, then we are making sure that we are picking the best element. So whether their particular adjacent station was selected or not, we pick the best one. And in this way we pick the best one from this, we pick the best from this, we pick the best from this, and we maximize it, right, to make sure that we have the better result. So this is when this particular node is, or when this particular node I is not included. Now, how to compute when this particular node is included? Now, if the same thing, if we are including this particular node, then we cannot include these node. And by this, it doesn't say that we cannot include the DP computation. We can simply not include this node. So for every node, remember, we have dp0 of dp1. So for every child node, we cannot, earlier what we are doing, we are selecting dpj of 1 because we can include that particular child node because we are not including the parent node. But at this time we are including the parent node. So as we are including the parent node, we cannot include the child node, meaning we cannot involve this in our solution, but we can involve this particular volume. So what we'll do is that the volume of the ith node, because we are including this node in our solution, along with that we're gonna do a sum of all the children. And this time, while summing up the children, we don't have any choice. We can only have dpj of 0. Why? Because we are including the parent node, and that is why we cannot include their children node, and that is why we cannot deal with any of the solution where the children node is included, and that is basically dpj of 1, because dp1 deals with the solution where the node is included. So we cannot deal with any of the solution in the children node where they are included. So that is why we are only dealing with those solution of the children node where those particular node are not included, or basically excluded. So that is why these are the two basic dp values. So this is how you will gonna compute dp's of these two nodes, or basically as a dp solution of a particular node, and you will gonna return it. So once this computation is done, you will gonna return it, and this will happen for each and every node in the tree, right? And now what will happen is that I'm just gonna draw a tree here. What this will happen is that, so the structure is like this. So for every node, this dp will be computed. It will start from, because we are doing a DFS, it will gonna come to the lowest level, right, from the top. Now it will gonna return, right? It's a DFS, so it returns the node here, it goes here, it returns here. Once the children are sorted, we compute the dp of this one, it returns here, and same thing happens here as well. The children values will be returned, and once all the children values are returned, the final value will be returned from the root node. And this final value will be, there will be two values, dp0 of root, dp1 of root. Means the best solution when the root was excluded, and the best solution when the root was included. When everything is done, you get these two values from your recursive method, and what you will do, you will gonna return the max of these two, right? You return the max of dp0 dp1 of the root, and this will be your end result. That's it. This is the only thing which we have to do, right? So this looks complex, but if you look at a dp level, or like if you look at per node level, you're gonna like find this interesting, and it's understandable. Now I have just written a code solution here. So what I'm gonna trying to do here is that I'm just like trying to explain what the recursive or the DFS method which we looked previously. So here we can see that there is a DFS method here. So what it does is that this is being called initially from the root, and this what it does is that it is gonna, like, first it traverse all the children nodes, right? And then for every children node, it computes the dp value, right? Initially we have this dp value, which is like 2 value for this, but for this current node, right? And where dp1 is the one where this node is included, and since this node was included, we have like make sure that the volume of this particular node is added here, right? So the volume of the people of this particular node is added to the solution. And dp0 was, since dp0 was the solution where the node is not included, we will keep it as it is, and by default the values are 0 of the integer in Java. So dp0 will stay 0, dp1 will be the volume. Now what will happen is that we're gonna traverse its children. So basically what we are doing, we are traversing the adjacent nodes here, right? So when we are traversing adjacent nodes at the below level, we are just seeing that if the particular node is visited or not. It's because we should not accidentally go to the root node, right? We should always go to the unvisited children node. So we are making sure that the particular node is unvisited, right? So unvisited node, and after that, once we have that particular node unvisited, we are computing the same thing for that particular child node. So the DFS will gonna go all down and compute that for that children node, and we'll again get the DP child result. So this method returns an integer array where this array will have two values. So DP child will have two values. First will be the values where that particular child was the maximum volume when that particular child was included, and the another value will be the maximum volume of the node when that particular child is excluded. And that's what we talked about in the DP solution. So first solution was DP of 0, where we are excluding the current node, that is the node. And if since we are excluding that, we can check both the values. We can also check the solution where the children was included. We can also check the solution where the children was not included, and we are picking the maximum value, and we are storing that in our current solution set. Second thing is when the current node is included, and since the current node is included, we have already added the volume of that particular node into the solution set, and now we cannot pick up this one where the children node was included, because hey, there was a rule that you cannot pick up the neighboring nodes. So since we have already included the parent node, we cannot include the children nodes, and that is why we will go ahead and we will gonna put this one where the maximum volume of people when the child node was not included into our solution set. And in this way we build up these two solution sets, dp0, dp1, and we return this dp, right? So in this way what will happen is that when we will call that, so suppose we have a root node, right? Suppose we have a root node here, it's just for the sake, and we call DFS on this root node and on the rest of the values. So we have the tree sorted and the volume of the node. Then we will have the final result here, right? And this result will be nothing. This will have two values, res 0, which is basically the maximum volume of people when root is excluded, right? And we will have another res1, which is nothing but the maximum volume of people when root is included, right? And when you want to find the best result, you will do basically we're gonna print the maximum, right? We're gonna res0 and res1, or basically dp0, dp1, we're gonna print the maximum, because that's what we are interested in. We are interested in the maximum volume, or basically we are interested in maximizing the volume of the people. So that is why we will pick up the maximum value among the two in the final result, and that will give us the final answer to this problem. This is the way it is tend to be solved. The solution looked big, the solution looked complex, but if you'll see the code, it will be pretty simple. So the only thing we have to do is to have to basically visualize the problem, visualize the structure in our mind, how the structure or how the tree structure could look like, and how we can perform DP at a particular node level so that we can reach to a final result, right? This is the entire problem. I guess you folks like the solution walkthrough.